morning, everybody. I'm Parag Kulkarni from University of Fischer, and today I'm going to talk about catalytic dechlorination of fluorocarbons from supported metal catalysts. And particularly, I'm going to concentrate on a different way of producing some useful compounds from these CFCs through carbon-carbon coupling reactions. So, as you all know, fluorocarbons, mainly due to the chlorine atom present in these molecules, are responsible for the depletion of ozone layer. So various ways are being investigated to convert these fluorocarbons into useful compounds. And amongst all these routes, catalytic dechlorination to selectively remove chlorine atoms and produce hydrofluorocarbons, which can replace CFCs in many of their applications, is the most promising route. For example, catalytic dechlorination of CF2Cl2 has been studied thoroughly over the past decade, and most of these studies were targeted to selectively remove chlorine atom from this molecule to produce CF2H2. And it's a general agreement that palladium, either supported on aluminum trifluoride or activated carbon, is the best catalyst to do this reaction. And another relatively less investigated way to produce industrially important compounds through this reaction is carbon-carbon coupling reaction. And even though reporters have reported some selectivity towards some coupling compounds such as ethylene, ethane, even in some cases tetrafluoroethylene, a systematic study of different elementary steps which lead to either coupling product or hydrogenolysis products is still absent, and we hope to throw some light on this issue. And one important thing I want to stress here is basically we are looking at a different way of producing useful fluorinated compounds from CFCs. For example, starting from CF2Cl2, we are interested in forming important monomers such as tetrafluoroethylene or ethylene on the surface of a catalyst at industrially relevant temperatures. The major issues involved in this type of reaction are first, that dissociation of carbon-halogen bond should take place to produce either fluorocarbene or carbene species on the surface of the catalyst, and these species should couple with each other as against undergoing hydrogenation or hydrogenolysis. These issues have certain mechanistic analogy with the famous Fischer-Tropsch synthesis. In case of Fischer-Tropsch synthesis, researchers believe that formation of carbene species takes place on the surface of the catalyst, and depending upon the properties of the catalyst, either they can undergo polymerization to produce higher molecular weight compounds, or they can undergo hydrogenation. In case of CF2Cl2 hydrogenolysis also, fluorocarbene and carbene species are the possible intermediates which can either couple to form the fluorinated products or higher molecular weight products, or they can undergo hydrogenation. And now the question is, what is the best catalyst to do this type of chemistry? To answer, as a first step to answer this question, we started with group 8 noble metals, which are ruthenium, rhodium, palladium, osmium, iridium, and platinum. Basically, group 8 noble metals, they are known to dissociate carbon-halogen bond. At the same time, they can dissociate hydrogen also. And the products that were formed in this reaction, they are grouped as C1 products, or the products with only one carbon atoms, and the more interesting coupling products. And the focus of this investigation was understanding how the type of the metal influences the selectivity towards these different elementary steps, which will either give us the C1 products or the more desired coupling products. Now I'll just quickly go through the experimental conditions. Basically, the reaction was carried out in a flow system containing a microreactor and at near atmospheric pressures. The monometallic catalyst used were 0.58%. In case of bimetallic catalyst, the molar ratio of the active metal, which was palladium or platinum, to the other metal was obtained from Calgon, which has very high surface area of around 1500 meters square per gram, was used as a support. And the reaction temperature was 250 degrees centigrade. The CFC to hydrogen ratio that I am going to talk about today was 1:1, which is the stoichiometric ratio to produce tetrafluoroethylene from CF to CF2. And it should be noted that all these catalysts, they deactivated with time one stream, and the rate of deactivation, it decreased with time one stream, and after around 20 to 30 hours, the catalyst attained some kind of pseudo steady state, and the selectivities were compared at this steady state, where the convergence were in the range of 0.5 to 2 mole%. Now, as I told you earlier, the major C1 products those were produced are listed here. The CF2Cl2 can undergo total hydrogenolysis to produce methane. Selective removal of 2 chlorine atoms gives CF2H2. Removal of only 1 chlorine atom gives CF2HCl, or the interaction of chlorine species on the surface with the intermediate gives CHF3. Now, let's see how the type of metal influences the selectivity pattern towards these products. First, these are the selectivities towards the highly halogenated compounds such as CHF2Cl and CHF3. And as you can see, in each triad, the metals towards the left, ruthenium, rhodium, and osmium and iridium, they show very high selectivity, around 40% towards these halogenated products as compared to palladium and platinum. But now if we add in selectivity towards more hydrogenated compounds, exactly opposite trend was observed. If you see the blue bars and green bars, selectivity towards CH2F2 and CH4, combined selectivity towards these two products, it increased as we go from ruthenium to palladium and osmium to platinum. That trend is more clearly shown in this triad, in where platinum produces mainly methane. And that was about the C1 selectivity, but if you remember, we are more interested in the coupling selectivity, and this shows the selectivity towards the halogenated coupling products, tetrafluoroethylene or CF2CH2, which are produced by interaction of fluorine and carbene species. And again, you can see that ruthenium, rhodium, and osmium and iridium, they show at least some selectivity towards these fluorinated compounds. Even if the selectivity was less than 5 mole%, it suggests that the pathway of CF2 coupling is taking place on this catalyst as against palladium and platinum under the reaction conditions. Now, if we add the coupling selectivity towards hydrocarbons, then the picture changes, and palladium supported on carbon was the best catalyst to produce these coupling products. Almost 75% selectivity under the reaction conditions towards these hydrocarbon coupling products. Then ethylene was almost 40% in this case. And in case of platinum also, it showed selectivity towards only hydrocarbon coupling products, but the total selectivity towards this coupling products was very less. Now, what is the reason for such kind of selectivity pattern? What we have seen is the metals in the left, they are producing halocarbon and palladium and platinum, they are producing more hydrocarbons. So, based on the heats of reaction of bulk chloride reduction, and also some reports, those are in the literature, about the nobility of these metals along the periodic table, it's known that metals in the left in these triads are more oxophilic or more easily oxidized, and the expected metal halogen bond strengths, they will decrease as we go from ruthenium to palladium and osmium to platinum. So we can expect, in case of surface coverages also, the surface coverage will decrease as we go from ruthenium to palladium and osmium to platinum. And that was what we observed in pathway of further hydrogenolysis of the CF2 species to CH2 species is dominant. That is what we see in the product distribution. And now in case of palladium, the CH2 species are undergoing coupling to produce ethylene, but in case of platinum, it is produced, they are producing only methane. One of the possible reasons that can be lower availability of hydrogen atoms on the surface of palladium catalyst, maybe due to the higher halogen coverage, or the halogen is modifying the properties of palladium somehow, so that it's giving more selectivity towards these coupling products. Similar reports are there in the literature. Even in case of Fischer-Tropsch synthesis, if halogen atoms are present on the surface, then the selectivity towards higher molecular weight compounds was increased in some cases. But there are also reports that if you have more halogen on the surface, then obviously they can interact with the intermediates in the main reaction and produce side products. And that is what might be happening in our case also, where we expect more halogen coverage in case of the metals in the left, ruthenium, rhodium, osmium, and iridium. In case of these metals, the pathway leading to hydrogenolysis of CF2 species to CH2 or hydrogenation of CF2 to CH2F2 is not dominant. But in this case, these fluorocarbene species, they can either react with the fluorine atoms on the surface and produce CHF3, or they can react with chlorine and produce CHF2Cl. And these were the major products that we observed on these four metals. And the pathway towards coupling of these two species was not that dominant. But if somehow we can modify the properties of the catalyst in such a way that the fluorine coverage on the surface will be just enough to inhibit hydrogenolysis or hydrogenation of fluorocarbene species, but at the same time it won't be very high so that they will interact with these fluorocarbene species itself and produce side products. In that case, it might be possible to achieve high selectivity towards this coupling compound to produce C2F4. And so now the question is how to get this optimum condition. Until now we have seen, what we have seen is on ruthenium, rhodium, osmium and iridium we see very high halogen coverage. We expect very high halogen coverage as against on palladium and platinum. And we want something intermediate which will be optimal for coupling reactions. So can we obtain that by modifying somehow palladium or platinum catalyst? And in this case, group 1B metals such as copper or silver are the likely candidates to do such type of chemistry. And it's known that copper has more affinity towards halogen atoms than palladium and platinum. Also, copper can dissociate carbon-halogen bonds, but it cannot dissociate hydrogen readily, so it's not active on its own. And also, copper is known to form readily couple carbene species formed on the surface. And also, there are numerous reports in the literature how copper can influence the selectivity pattern of platinum through ensemble of electronic effects. So in this case also we can imagine a bimetallic type of catalyst surface where the halogen coverage will be controlled by hydrogen that is dissociated on the active metal, and the other metal can help dissociate carbon-halogen bond, and also it can modify the properties of the active metal, and maybe it's possible to get this desired coupling product in this case. Now based on this hypothesis, we studied platinum copper, or we modified platinum with copper. The coupling products. But like dramatic change was observed when we modify copper with platinum. During some initial hours of time on stream, it showed very high selectivity towards ethylene and even some C3 and C4 compounds. These were all hydrocarbons, and it shows that these selectivities are going through some kind of maxima, indicating something is changing on the surface, which might well be the halogen coverage, and again indicating that certain type of optimum halogen coverage is necessary to produce coupling, to achieve high selectivity towards this coupling product. And now, as the selectivity towards this hydrocarbon decreases, as we have seen in the earlier slide, the selectivity towards C1 halocarbon increase in case of this catalyst, and also the selectivity towards the fluorinated coupling product CF2 increased, and in this case is almost reached around 15%, and again it goes to a maximum, again indicating some kind of optimum fluorine coverage is required or achieved in that case. So here I want to again stress a point that our first objective was production of these, or achieving more selectivity towards tetrafluoroethylene from CF2, and in case of platinum copper catalyst, we are getting almost 15% selectivity as compared to which is like 5 times more as compared to the which was on monometallic catalyst. So this is a quick summary of the platinum copper catalyst. Platinum mainly produced methyl copper was inactive under the reaction condition, but in case of platinum copper, first it showed higher selectivity towards hydrocarbon coupling products, but with time on stream, the selectivity towards both C1 and C2 halocarbon products increased. Then I'll quickly show the selectivity pattern of when we modify the other group 8 noble metal palladium with copper. Here also you can see that selectivity towards the halogenated products CHF2Cl and CHF3 was higher as against on monometallic catalyst, again indicating might be higher surface halogen coverage. And if you remember, palladium was our best catalyst to produce coupling products, but which were very high selectivity towards on the hydrocarbons. But when we modify the copper, the initial selectivity towards the hydrocarbons was even more than what we got on monometallic palladium. But with the time on stream, the selectivity towards this hydrocarbon dropped as maybe due to increase of halogen coverage, and as we saw in the earlier slide, the C1 halocarbon selectivity increased, and the selectivity towards C2F4 that we got in this case was around 5%. So again, the summary case of palladium copper catalyst. Again, we see some sort of halogen increase in halogen availability on the surface, and palladium copper shows initial high selectivity towards coupling and selectivity towards both C1 and C2 halocarbon. It increases with time on stream. So finally, I would like to tell the conclusions. The product distribution on group 8 metals shows that these metals somehow influence the surface coverage of hydrogen and halogen atoms, and hence the selectivity pattern in CF2 Dechlorination reaction. Also, the product distribution is indicating that certain kind of optimum halogen coverage is necessary to achieve high selectivity towards both hydrocarbon and halocarbon coupling products. And the most important point is it is possible to obtain higher selectivity towards halogenated coupling products such as C2F4 by modifying the properties of palladium or platinum with the 1-weak group metal. And I think more research is required to be done in this case to get a to achieve more optimum conditions, more optimum loading of the catalyst to get rid of some kind of transition periods, etc. But the main point is it is indeed possible to get selectivity towards this desired fluorocarbon products. And finally, I would like to conclude my talk by acknowledging National Science Foundation and DuPont for their financial and technical support. And thank you all for paying attention. And I will be happy to answer your questions.
Questions? Please. I have two questions. First, what is the evolution of the surface composition of your biometallic catalyst during the reaction, the course of the reaction? Is it necessary to have a close contact between copper and platinum or copper and palladium? And second question, you show the evolution of your selectivity. What about the reactivity, the conversions?
Okay. About the first question about the bimetallic catalyst, what exactly was it? You were interested in whether the platinum and copper should be close enough or so. Actually, I'm not. The evidence for the surface composition is I don't have at this point, but some colleagues in my group, they are also working on the how exactly the copper is influencing the active metals such as platinum, and they have found some electronic effects. It's influencing both by electronic and ensemble effects. And about the rates, I did not present the. I have the activities of this group at metal catalyst, which shows that. Anyway. Palladium had these are for the two CFC to hydrogen ratio, and the activities they were calculated as moles of reactants reacted per gram of metal per second, and it shows that palladium and platinum were the most active in this case. But our selectivity comparison we made between 0.5 to 2%.
Gonzalez Tulane, you showed that the activation, but I don't think you said anything about regeneration. You regenerate your initial catalyst to initial selectivity. How do you supposedly probably exploit it with the fluoride?
Yeah.
How do you spin it off?
We actually don't regenerate it, and we are not concentrating. There should be some way by hydrogenation or something like that. But you must also remember that the support is also activated carbon, and certain vigorous regeneration conditions we cannot apply because that can lead to change in the dispersion or even maybe oxidation of the support itself or something like that. So we are not really concentrating on regeneration issue.
But sooner or later, this is an important.
Yeah, that's true. Yeah, I'm just trying to make a point that it is indeed possible to do such type of chemistry.
Did you perhaps investigate different kind of charcoal, or you just concentrate?
Until right now, we are just only concentrated on this type of activated carbon, but that might be focus of our further research, because it's also known that the nature of activated carbon, it